Achieving a H1 grade in Leaving Cert Maths is an ambitious objective, representing the pinnacle of success on the exam. It's known for being devilishly difficult to obtain, but in this video I'll show you that it might be easier than you think. I'll demonstrate and guide you through the exact knowledge required to achieve a H1 grade. Counterintuitively, the hardest and longest questions in Leaving Cert Maths often carry the fewest marks. Because of this, reaching a H1 target is more attainable than you might realise. Join me as I guide you on your mathematics education journey. Who knows, it might even get you to the pinnacle of maths excellence, that elusive H1 in Leaving Cert Maths. In the 2023 Leaving Certificate exams, the maths papers were divided into two sections. In section A, you had to answer 5 out of 6 questions, worth 30 marks each. In section B, you had to answer 3 out of 4 questions, worth 50 marks each. All in all, both sections were worth 150 marks, bringing the total to 300 marks for the paper. To achieve the H1 threshold of 90%, you would need to score at least 270 marks. After analysing the paper, I've pinpointed the easiest and most effective way to reach this target. Solving the highlighted questions would have secured a H1 grade. In this video, I'll guide you through the step-by-step solutions for each of these questions. This will demonstrate the minimum knowledge required to obtain a H1. If you can follow along and understand my explanations, then you can step into your own exam with confidence, knowing that you have the potential to achieve a H1 grade. In question 1, we are presented with a spinner that contains 12 sectors. 5 sectors are labelled with €6, 3 sectors are labelled with €9, and the rest are labelled with €0. In a game, a player spins the wheel and wins the amount of money that the arrow lands on. In part A, we're told that Fiona plays the game a number of times. We need to find the probability that she gets a €6, then a €9, then a €6 the first 3 times she plays. 5 out of the 12 regions are labelled with €6, so on an individual spin, the probability you get €6 is 5 over 12. 3 out of the 12 regions are labelled €9, so on an individual spin, the probability you get €9 would be 3 over 12. In this question, we need 3 things to happen. We need €6 on the first spin, €9 on the second spin, and €6 on the third spin. We can find the probabilities of each of these events individually. There's a 5 out of 12 chance to get €6 on the first spin, 3 out of 12 to get €9 on the second spin, and 5 out of 12 to get €6 on the third spin. In probability, the word "and" typically corresponds to multiplication. So here, we need to multiply together the 3 individual probabilities. This comes out as 25 over 576. When we write this as a decimal, rounded to 4 decimal places, we get 0.0434. In part B, we're told that Rowan also plays the game a number of times. We need to find the probability that he gets €9 for the 3rd time on the 8th time that he plays. Well, there's 2 things that need to happen here. Rowan must win €9 exactly twice in the first 7 spins, and then win €9 on the 8th spin. On the previous page, we showed that there was a 3 out of 12 chance of winning €9 on any individual spin. So the probability of getting €9 on the 8th spin would be 3 over 12. The probability of getting €9 exactly twice in the first 7 spins is a bit harder. Here, we'll have to use the binomial distribution formula. N choose R times P to the R times Q to the N minus R. Here, N refers to the total number of trials. Since we have 7 spins, N is equal to 7. R is the amount of times we want our event to happen. Since we want €9 exactly twice, we will have R equal to 2. P is the probability that your event occurs on an individual trial. Here, there's a 3 over 12 chance we get €9 on an individual spin. So P is 3 over 12. Q is the probability that your event does not occur on an individual trial. We'll always have Q equal to 1 minus P. Here, Q is equal to 1 minus 3 over 12, which is 9 over 12. So, after subbing in, we get 7 choose 2 times 3 over 12 to the power of 2 times 9 over 12 to the power of 7 minus 2. When we type this into our calculator, we get 5103 over 16384. The word AND corresponds to multiplication, so to get our final answer, we must multiply this by the 3 over 12 we obtained earlier. Rounded to 4 decimal places, this gives us an answer of 0.0779. In part C, we are told that Olga plays the game 2 times. We need to find the probability that Olga gets less than €16 in total. Well, when we think about the structure of the game, it's quite difficult to win at least €16 when you play the game twice. On each individual spin, you'll either earn €9, €6 or €0. The only way that you could end up with more than €16 is if you got €9 both times. A 9 and a 6 would give you €15, which isn't enough. So, the only way to get at least €16 is to get €9 on the first spin and €9 on the second spin. There's a 3 out of 12 chance to get €9 on an individual spin, so the probability here comes out as 3 over 12 times 3 over 12, which is 1 over 16. This is the probability of getting €16 or more in your first 2 spins. To find the probability that we get less than €16, we simply have to subtract this number from 1. This gives us 1 minus 1 over 16, which is 15 over 16. Written as a decimal with 4 decimal places, this comes out as 0.9375. In question 3a, we're given the coordinates of 3 points and asked to find the area of the triangle with these vertices. There's a result in the formula book which says that the area of a triangle is a half times the absolute value of x1, y2 minus x2, y1. However, there's an important caveat here. To use this formula, we must translate the points so that one of them becomes the origin, 0, 0. Here, I'll perform a transformation to our first point, 4, 6, so that it gets mapped to 0, 0. We begin with an x-coordinate of 4, and we want an x-coordinate of 0. So the shift here is minus 4. We start with a y-coordinate of 6, and we want a y-coordinate of 0, so the shift here is minus 6. So the overall translation is minus 4 to the x-coordinate and minus 6 to the y-coordinate. This translation should also be applied to our other 2 points, minus 3, minus 1, and 0, 11. Minus 3 minus 4 is minus 7, and minus 1 minus 6 is also minus 7. So minus 3 minus 1 gets translated to minus 7 minus 7. This gives us the x1 and y1 value for our formula. 0 minus 4 is minus 4, and 11 minus 6 is 5. So 0, 11 gets translated to minus 4, 5. This gives us the x2 and y2 values for the formula. Now, let's sub in our values. x1 is minus 7, y2 is 5, x2 is minus 4, and y1 is minus 7. When we perform the calculation inside the absolute value, it comes out as minus 63. To find the absolute value of a number, we turn it into its positive version. So the absolute value of minus 63 is plus 63. A half times 63 is 31.5, so the final answer for the area of the triangle is 31.5 square units. In part B, we're presented with 2 points, A and B. We must show that the midpoint of the line segment AB is a specified value. Well, the formula book contains a result about the midpoint. It's equal to x1 plus x2 over 2, comma, y1 plus y2 over 2. Our first point is A, which is equal to minus 1, comma, k. We'll label the minus 1 as x1 and the k as y1. Our second point is B, which is equal to 5, comma, L. We label the 5 as x2 and the L as y2. Let's sub these values into the midpoint formula. The x-coordinate can be simplified here. Minus 1 plus 5 is 4, and when we divide this by 2, we get 2. So we found that the midpoint is 2, comma, k plus L over 2. These are precisely the coordinates we needed to obtain. In question 4a, we're told that the circle C has equation x minus h all squared plus y plus 3 all squared is equal to 12. In part I, we must write down the centre and radius of the circle. There is a result from the formula book which will help us out here. If we let h, k be the centre of the circle and r be the radius, then the equation of the circle will be x minus h all squared plus y minus k all squared is equal to r squared. Matching this formula with the equation we were given, we have a h in the slot of the h. We have a plus 3 in the slot of the minus k. And we have a 12 in the slot of the r squared. This gives us three equations. H is equal to h, minus k is equal to plus 3, and r squared is equal to 12. Changing the signs of both sides, minus k equal to plus 3 implies that k is equal to minus 3. Square rooting both sides, r squared equal to 12 implies r is equal to the root of 12. This means that the centre, h, k, comes out as h, minus 3. And the radius, r, is equal to root 12. In part 2, we're told that the perpendicular distance of a given line to the centre of the circle C is 5 units. We need to use this to work out two possible values of h. This question involves a perpendicular distance. The first step will be to open up our formula book and look this up. There's a result that says the perpendicular distance from the point x1, y1 to the line ax plus by plus c equal to 0 is the absolute value of ax1 plus by1 plus c divided by the square root of a squared plus b squared. We're told that the perpendicular distance is 5 units, so we should set this expression equal to 5. The line that we're given can be written as 1x minus 4y plus 7 is equal to 0. The point that we have is the centre of the circle. In the previous part of the question, we found that this was h, minus 3. In the formula, a refers to the number in front of the x. So here, a is 1. b is the number in front of the y, so here b is minus 4. c is the constant term, so c is equal to 7. x1 and y1 refer to the coordinates of the point, so here x1 is h and y1 is minus 3. Let's sub these values into our formula. From here we can simplify. 1 times h is h. Minus 4 times minus 3 is plus 12, and then when you add on the 7, you get plus 19. 1 squared is 1, and minus 4 squared is 16, so underneath the square root, we get 1 plus 16, which is 70. We can get rid of the fraction on the left if we multiply both sides by root 17. This tells us that the absolute value of h plus 19 is equal to 5 times the root of 17. The absolute value of the positive and negative versions of a number both come out to the same thing. So there's two options for the expression inside the absolute value. Either h plus 19 is equal to plus 5 root 17, or h plus 19 is equal to minus 5 root 17. Focusing on the first case, subtracting 19 from both sides gives us h is equal to plus 5 root 17 minus 19. In the second case, subtracting 19 from both sides gives us h is equal to minus 5 root 17 minus 19. So there's the two solutions for h. In question 5, we're told that Rowan has a large number of cubes. Some are red, some are green, and the rest are blue. Rowan performs the following experiment. He picks 5 cubes at random, he records the colours of the cubes, and then he replaces them. He repeats this process 7 times. In the table that we're given, the 7 trials are labelled with the letters from A to G. Looking at the column of an individual trial tells us how many cubes of each colour there were. For example, in trial D, there were 2 red cubes, 3 green cubes, and 0 blue cubes. In part I, we must work out the mean and standard deviation of the number of red cubes. Well, looking across the 7 trials, the number of red cubes were 0, 3, 2, 2, 4, 5, and 1. We'll need to find the mean and standard deviation of this data. Thankfully, modern-day calculators can find these quantities for us. If you go to statistics mode and type in our data, then the calculator will return the mean and standard deviation for you. Rounded to 1 decimal place, the mean will come out as 2.4 and the standard deviation will come out as 1.6. If you want more details on how to do this calculator work, check out the video linked in the description. In part 2, we must work out the correlation coefficient between the number of red cubes and the number of green cubes. Again, this will boil down to calculator work. This time, there'll be 2 lists of data we'll need to input. For the x data, we should put in the values for the number of red cubes. 0, 3, 2, 2, 4, 5, 1. For the y data, we should input the values for the number of green cubes. 4, 2, 0, 3, 0, 0, 2. Once you've performed the necessary steps, your calculator will return the correlation coefficient for you. Rounded to 3 decimal places, it comes out as minus 0.762. In part 3, we're told that Rowan repeats the experiment a large number of times. We must explain why we would expect the correlation coefficient between the number of red cubes and the number of green cubes to be negative. Well, the core idea behind a negative correlation is that when one quantity goes up, the other quantity will go down. In this experiment, Rowan picks exactly 5 cubes on each trial. This means that the red cubes plus the green cubes plus the blue cubes must be equal to 5. If there's a large number of red cubes, then there won't be much space left over for the other 2 colours. This means we'd expect a small number of green cubes. As an illustration, if the number of red cubes was 5, then there's nothing left over for the green cubes and blue cubes. So if red cubes equals 5, then it must be the case that green cubes is equal to 0. Since larger numbers of red cubes correspond to smaller numbers of green cubes, we have a negative correlation between the two quantities. In part B, we're presented with a cuboid that is made up of a large quantity of small cubes. The width of the cuboid is 5 units, the height is 4 units, and the depth is 3 units. We are asked to consider the number of faces each small cube has exposed on the outside. As an example, the cube in the top right corner has 1, 2, 3 faces on the outside. The task here is to count up how many small cubes have 3 faces on the outside, how many have 2 faces on the outside, how many have 1 face on the outside, and how many have no faces on the outside. One of these values is filled in for us already. We're told that there's 22 small cubes with 1 face on the outside. So, if we're trying to look at the cubes with 3 faces on the outside, you'll notice that this only happens at a corner piece. I've coloured these in purple in the diagram. There's 4 corner squares on the top layer, and there'll be another 4 corner squares on the bottom layer. It's worth pointing out that one of these corners is hidden from view in the diagram. 4 plus 4 is 8, so we end up with 8 small cubes with 3 faces on the outside. The cubes with 2 faces on the outside correspond to the non-corner pieces which appear along one of the edges of the cuboid. I've coloured these in orange. If we focus on the top layer of the cube, we have 1, 2, 3, 4, 5, 6, 7, 8 orange cubes. By symmetry, there'll be 8 orange cubes on the bottom layer. Focusing on the 2 middle layers, you'll notice we have orange cubes stacked in towers of 2. 3 of these towers are visible. 1, 2, and 3. There'll be a 4th tower hidden behind view below this back left corner. Each of these towers contains 2 orange cubes, and we have 4 of them, so this gives us 4 times 2, which is 8 orange cubes across the 2 middle layers. 8 plus 8 plus 8 is 24, so we end up with a total of 24 cubes with 2 faces on the outside. The only thing left is to find the number of small cubes with no faces on the outside. Well, the dimensions of the cuboid are 5 units, 3 units, and 4 units. The total number of cubes will be 5 times 3 times 4, which is 60. We've already found the number of cubes with 3 faces, 2 faces, and 1 face on the outside of the cube. The number of cubes with no faces will simply be the leftovers that are needed to make up a total of 60. We can find the leftovers which are needed by subtracting each of the other numbers from 60. So we get 60 minus 8 minus 24 minus 22. This comes out as 6. In question 6a, we're given a statement and we must determine whether it's true or false. The statement is, 2 angles are vertically opposite if and only if they are equal in size. The phrase, if and only if, means that the implications must go in both directions. For this statement to be true, it would have to be the case that two angles being vertically opposite implies that they are equal in size, but also if two angles are equal in size, it implies that they're vertically opposite. If we think a bit about this second implication, we run into some issues. It is not the case that angles being equal implies that they're vertically opposite. To illustrate this, I've drawn a little diagram. The angles A and B here are alternate angles, which means they are equal. However, they are not vertically opposite. So we've shown that it's possible to have two angles equal in size, which are not vertically opposite. This means that the statement is false. In part B, we're presented with two diagrams of a rectangle, ACEG. In diagram A, various sides and angles have been labelled for us. We're told that GA has a length of 90 centimetres, AB has a length of 20 centimetres, and BC has a length of 30 centimetres. We've also been told that three of the angles in this diagram are equal. They've all been labelled with theta. In diagram B, the lines GE and BD are extended to meet at a point H. These two diagrams will be helpful for the questions on the next page. In B part I, we must prove that the length of FE is equal to the length of EH. And we're told to use congruent triangles in our proof. In diagram A, the angle DBC was labelled with theta. Since the lines GH and AC are parallel, we can use alternate angles to deduce that EHD is equal to theta. We're told that ACEG is a rectangle. This means that the angles in each of the corners must be 90 degrees. In particular, the angle FED will be 90. We know that FH is a straight line. Since angles on a line must add to 180 degrees, we know that the angle FED plus the angle HED must sum to 180. It follows that HED will be 180 minus the angle FED. We already found that this was 90, so we end up with 180 minus 90, which is 90 degrees. Now that we've filled in some of our angles, we're ready to compare the triangles EFD and EHD. The angle EFD is equal to the angle EHD because they've both been labelled with theta. The angle FED is equal to the angle HED since they're both 90 degrees. Since the three angles in a triangle always add up to 180 degrees, once you know two angles are equal, it must be the case that the third angle is equal. It follows that the angle FDE is equal to the angle HDE. The triangles also share a common side, ED. Since we've shown that the angles on each end of this side are equal, it follows that the triangles are congruent by ASA, angle side angle. In congruent triangles, the side lengths are equal. Since FE and EH are both opposite the green angle, it follows that the length of FE and the length of EH are equal. In part 2, we must find the size of the angle theta. To help us here, I've copied out the measurements from diagram A. We were told that GA was 90 centimeters, AB was 20 centimeters, and BC was 30 centimeters. This information can be used to fill in some other side lengths. The first thing to observe is that AFHB is a parallelogram. We know that AB is 20 centimeters and opposite sides in a parallelogram are equal, so it follows that FH is 20 centimeters. In the previous part of the question, we showed that FE and EH were equal in length. This means that the 20 centimeters for FH is split into two equal parts, 10 centimeters for FE and 10 centimeters for EH. Focusing on the original rectangle, the bottom side, AC, has a length of 20 plus 30, which is 50 centimeters. It follows that the top side, GE, must also be 50 centimeters. Since FE is 10 centimeters long, there's 40 centimeters left over for GF. Now, if we draw our attention to the theta in the right angle triangle AGF, you'll notice that the side opposite theta is GA, which is 90 centimeters. The side adjacent to theta is GF, which is 40 centimeters. In a right angle triangle, the tan of an angle is equal to the opposite over the adjacent. So we know that tan of theta must come out as 90 over 40. To find theta, we just need to get rid of the tan. We can do this by taking tan inverse of both sides. When we calculate tan inverse of 90 over 40, we get 66.0375. Rounding this to the nearest degree gives us our final answer that theta is equal to 66 degrees. In question 7a, we're presented with a diagram of a sloped road, AB. In this diagram, AC is horizontal and BC is vertical. We're told that AB is 70 metres and that BC is 9 metres. We are presented with a definition for the gradient of the road. It's defined to be the length of BC over the length of AC, written as a percentage. We need to find the gradient of the road correct to the nearest percentage. To use a definition of the gradient, we need to know two things: the length of BC and the length of AC. BC has been given to us directly. It's 9 metres. AC is not given to us, but we can find it using Pythagoras' theorem. This states that in a right angle triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. The hypotenuse is the side opposite the right angle. Here, that's the 70 metres. This gets labelled with C in the theorem. The other two sides get labelled with A and B. Here, I'll label the length of AC as A and label the 9 as B. Subbing these into our theorem, we get 70 squared is equal to the length of AC squared plus 9 squared. 70 squared is 4,900 and 9 squared is 81. To get rid of the plus 81 on the right, we can subtract 81 from both sides. When we perform the calculation on the left, it comes out as 4819. Now, to get rid of the square, we can square root both sides. This tells us that the length of AC is equal to the root of 4819. We now know everything we need to calculate the gradient. By definition, the gradient is the length of BC over the length of AC. The length of BC is 9, and the length of AC is the root of 4819. Typing this fraction into our calculator gives us 0.12964747. We were asked to present the gradient as a percentage. To convert from decimal to percentage, we multiply by 100 and write in a percentage sign. When we round this off to the nearest percent, we come to the final answer that the gradient is 13%. In part B, Olga is looking at a point at the top of a hill, H. Olga wants to find the vertical height of this point. There's 2 points on the ground, R and P, which are 20 meters apart. And we know that the angle of elevation from R to H is 17 degrees. We're also told that the angle ORP is 88 degrees and the angle RPO is 87 degrees. We must use this information to find the distance from O to H. There's 2 triangles in our picture, ROH, which I've coloured in blue, and RPO, which I've coloured in red. The side that we're trying to find, OH, appears in the blue triangle. Unfortunately, we don't know much about this triangle. All we have is 2 angles, and we don't know any of the side lengths. In contrast, we know a bit more in the red triangle. Here, we have 2 angles and 1 side. An important thing to observe here is that the triangles share the side RO. If we can use the red triangle to find the length of this side, it will give us new information about the blue triangle and hence help us on our way to the final goal. The first thing to observe is that we know 2 out of the 3 angles in the red triangle. Since the angles in a triangle must add to 180, the third angle will be 180 minus 88 minus 87, which is 5. From here, we can find the length of the line RO by using the sine rule. A over sine A is equal to B over sine B. Here, I'll label the 5 degrees as capital A. The side opposite this, the 20 meters, will be labelled as lowercase a. I'll label the 87 degrees as capital B, and the side opposite this, RO, will be little b. Let's sub these into our formula. To find the length of RO, we'll want to get rid of the division of sine 87. To do this, we multiply both sides by sine 87. When we perform the calculation on the left-hand side, we find that the length of RO is 229.16 metres. Now, let's turn our attention to the 17-degree angle in the blue right-angle triangle. The side we're trying to find, OH, is opposite this 17-degree angle. The side adjacent to the 17 degrees is the 229.16 we've just found. In a right-angle triangle, the tan of an angle is equal to the opposite over the adjacent. Here, the angle is 17 degrees, the opposite is OH, and the adjacent is 229.16. To find the length of OH, we'll want to get rid of the division by 229.16. We can do this by multiplying both sides by this number. From here, we can perform the calculation on the left-hand side and round to the nearest metre. This brings us to our final answer. The length of OH is 70 metres. In the next part of the question, we're told that Olga has done some tests to measure her lung capacity. When she is resting, we can model the volume of air, V, in her lungs after t seconds with the following function. V of t is equal to 2 minus 0.4 times the cosine of pi over 2t. Here, the volume is in litres and t is the time in seconds. An important thing to note here is that the expression inside the cosine is measured in radians. This means that we'll need our calculator in radians mode for the duration of this question. Along with this written description, we've been provided with a visual representation of the same information in the form of a graph. Here, the vertical axis represents the volume of air in litres, whereas the horizontal axis is representing the time in seconds. In part C, we must find the minimum and maximum values of our function. These have been labelled A and B in the graph. If we analyse the structure of our function, we'll notice that the 2 and the minus 0.4 are constants. They won't change depending on the value of t. The only thing that changes is the cosine pi over 2 times t term. This means that the minimum and maximum values of our function will occur at the minimum and maximum of this expression. A useful piece of background knowledge here is the following. The function f of x equal to cosine of x has a minimum value of minus 1 and a maximum value of plus 1. It turns out that cosine of pi over 2t will also have a minimum of minus 1 and a maximum of plus 1. Even though the expression inside the cosine is different, this only affects the speed at which the curve moves, not the minimum and maximum points. To find the minimum and maximum values of our function, v of t, all we have to do is sub in the minimum and maximum values of the cosine pi over 2t. In other words, we should replace this expression with minus 1 and with plus 1. When we put in minus 1, we get 2 minus 0.4 times minus 1. This comes out as 2.4. When we put in plus 1, v is equal to 2 minus 0.4 times plus 1. This comes out as 1.6. So the answer here is that the minimum value for our volume, A, is equal to 1.6, and the maximum value of the volume, B, is equal to 2.4. In part D, we're asked to think about the connection between v dashed of t, the derivative of v, and whether Olga is breathing in or breathing out. The most important thing to remember here is that at its core, a derivative represents a rate of change. Here, the derivative v dashed of t represents the rate of change of our volume, v of t. Well, when Olga is breathing in, the volume of air in her lungs will be increasing. If something is increasing, this corresponds to a positive rate of change. So here, the rate of change, v dashed of t, will be positive. On the flip side, when Olga is breathing out, the volume of air in Olga's lungs will be decreasing. When something is decreasing, this corresponds to a negative rate of change. So here, the rate of change, v dashed of t, will be negative. In part E, we must use the formula for v of t to perform some calculations. Here, each answer should be rounded to 3 decimal places. First, we must find the volume of air in Olga's lungs half a second after t equals 0. Well, half a second after t equal to 0 corresponds to t equal to a half. We want the volume of air at this time, and that's precisely what our function v of t tells us. It tells us the volume. So here, all we have to do is substitute in t equal to a half into our formula. This gives us 2 minus 0.4 times the cosine of pi over 2 times a half. Ensuring that our calculator is in radians mode, we can perform this calculation and obtain the answer 1.717157. Since we were asked to round to 3 decimal places, the final answer here is 1.717 litres. In part 2, we're asked to find the rate at which the volume of air in Olga's lungs is increasing half a second after t equal to 0. An important thing to pick up on here is that this question involves a rate of change. We're not looking at the volume itself, but rather the rate at which the volume is increasing. As we mentioned earlier, the derivative v dashed of t will represent the rate of change. Solving this question will first require us to calculate this derivative. We'll do this by differentiating our function v of t is equal to 2 minus 0.4 times the cosine of pi over 2t. Since additive constants differentiate to 0, the 2 will differentiate to 0 and simply disappear. Differentiating the minus 0.4 cosine pi over 2t is a bit more tricky. The first thing to observe is that the minus 0.4 is a multiplicative constant. This doesn't disappear, but it won't interfere either. It simply hangs on the side of our expression when we differentiate. So the main work here we'll be differentiating the cosine of pi over 2t. Since this is a layered expression, we'll need to use our chain rule when we differentiate. In the chain rule, we need to perform two differentiations, an inner differentiation and an outer differentiation. In this expression, the inner layer is pi over 2 times t. A constant times t just differentiates to the constant, so pi over 2t will differentiate to pi over 2. Now, looking at the outer layer, our expression is in the form of cosine of something. If we look at our formula book, we'll see that cosine differentiates to minus sine. Here, the something that we had inside the brackets was pi over 2t. So this comes out as minus sine of pi over 2t. Now that we've performed our two differentiations, we get our answer for the chain rule by multiplying together these two expressions. This means that the cosine pi over 2t will differentiate to pi over 2 times minus sine of pi over 2t. We've done the hard work now since we found our derivative v dashed of t. We can simplify our expression slightly by observing that the two minus signs will multiply together to give a plus, and also observing that 0.4 divided by 2 gives us 0.2. This brings us to the result that the rate of change at any time t, v dashed of t, will be equal to 0.2 times pi times sine of pi over 2t. We want to know the rate of change half a second after t equal to 0. In other words, we need the rate of change when t is equal to a half. To find this, all we have to do is sub in a half to our derivative. This gives us 0.2 pi times sine of pi over 2 times a half. Again, ensuring that our calculator is in radians mode, we can perform this computation to get an answer of 0.444288. Rounding to 3 decimal places brings us to our final answer of 0.444 litres per second. In question 9, Ava is looking at different ways to tile a region with shapes. We're considering two options: tiling with squares and tiling with regular hexagons. We're told that a square tile and a hexagonal tile each have an area of 140 centimetres squared. The first task is to work out the length of the side of the square tile, correct to 1 decimal place. Well, there's a well-known fact about squares which says that a square with a side length of L will have an area of L squared. We're told that the area is 140, so we can set L squared equal to 140. To solve for L, all we have to do is take the square root of both sides. We can use our calculator to compute the square root of 140. And when we round to 1 decimal place, we get our final answer that the length is 11.8 centimetres. In the next part of the question, we must find the side length of one of our hexagonal tiles. This is a bit trickier. Thankfully, we've been provided with a diagram with some helpful labels. In this diagram, the hexagon is split into 6 equal triangles. One of these triangles has 3 labels written in: a 60-degree angle and 2 sides marked as X. Since the hexagon contains 6 equal triangles, we can deduce that the area of the hexagon will be 6 times the area of one of these triangles. We know that the area of the hexagon is 140, so if we can write the area of a triangle in terms of x, we'll be able to use this equation to solve for x. To find the area of the triangle, we can use a result from page 16 of the formula book. It says that the area of a triangle is equal to 1/2 times A times B times sine C. Here, A and B refer to the lengths of 2 sides of the triangle, and C refers to the angle between these 2 sides. In the label diagram we've been given, we have 2 sides and the angle in between. To use our formula, we can let A be equal to x, B be equal to x, and C be equal to 60 degrees. Subbing these in gives us 1/2 times x times sine 60. X by x simplifies to x squared, and using our calculator, sine 60 becomes √3/2. To simplify further, we can multiply the 1/2 by the √3/2, and this gives us √3/4 times x squared. Now that we have an expression for the area of the triangle, we can write it into the equation we had and then solve for x. In our equation, the x squared is being multiplied by a constant, 6 times the square root of 3/4. To remove this multiplication, we should divide both sides by this number. We now know what x squared is equal to, so to solve for x, all we have to do is remove this square. We do this by taking the square root of both sides. We can use our calculator to compute the expression on the right-hand side. It comes out as 7.340710. We were told to round our answer to 1 decimal place, so the final answer here is that x is equal to 7.3 centimetres. In part B, Ava is considering a more complicated tile. Here, each tile consists of 2 parts. An arrowhead, A, B, E, D, which I've coloured in blue, and a quadrilateral, E, B, C, D, which I've coloured in red. In part I, we're provided with several side lengths. We're told that AD is equal to 8 centimetres, AE is equal to 6 centimetres, and ED is equal to 4 centimetres. In the diagram, one of the angles is labelled alpha, and we must show that alpha is equal to cosine inverse of 7/8. Well, if we take a look at the values we're given, they all live in the same triangle, AED. Let's focus in on this triangle. We know all 3 side lengths, and we're trying to find an angle. So all in all, we're working with 3 sides and 1 angle. This is precisely the setup we need to use the cosine rule. This says that a squared is equal to b squared plus c squared minus 2bc times the cosine of capital A. Here, capital A refers to an angle, and in our diagram that will be the alpha. Lowercase a is the side opposite this angle, and here a will be 4. B and C refer to the other two side lengths. Here we can let B be equal to 8 centimeters and C be equal to 6 centimeters. Let's sub these values into our formula. From here we can simplify a bit. 4 squared is equal to 16. 8 squared plus 6 squared comes out as 100. And minus 2 times 8 times 6 is equal to minus 96. The result we need to show has alpha all by itself on one side of the equation. So the target here will be to isolate the alpha. To start, we can get rid of the plus 100 by subtracting 100 from both sides. From here, we can simplify on the left. 16 minus 100 is minus 84. Next, we can get rid of the multiplication of minus 96 by dividing both sides by minus 96. Now, if we use our calculator to simplify the fraction on the left-hand side, it comes out as 7 over 8. Finally, to get rid of the cos, we need to take cos inverse of both sides. This tells us that alpha is equal to cos inverse of 7 over 8. This is precisely the result we needed to show. In part 2, we're told that the angles ADC and ABC are equal to 90 degrees. We must use this to work out the total area of the quadrilateral ABCD. A good place to start here is to focus in on the triangle ADC. This triangle makes up half of our quadrilateral, so if we can find the area of this triangle, we can simply double it to find the area of the quadrilateral. Well, we're told that the angle ADC is 90 degrees. In other words, it's a right angle. So we can use the results for sine, cos and tan in right angle triangles. We're trying to find the length of AC, and that corresponds to the hypotenuse in this triangle. Focusing on the known angle, alpha, the side AD, which is 8 centimeters, corresponds to the adjacent. Since we're working with the adjacent and the hypotenuse, we can use the result that cosine of alpha will be equal to the adjacent over the hypotenuse. In the previous part of the question, we found that alpha is equal to cosine inverse of 7 over 8. We've shown that the adjacent is 8 and that the hypotenuse is the side AC. Some nice cancellation happens on the left. The cosine will cancel the cosine inverse, so we're left with 7 over 8. Next, we can multiply both sides by the side length AC. And finally, we can divide both sides by 7 over 8. When we calculate 8 divided by 7 over 8 in our calculator, we get 64 over 7. Now that we know the length of AC, we have two side lengths and the angle in between. So we're ready to use our formula for the area of a triangle. A half times A times B times sine c. Here, we can let A be equal to the side length AC, which is 64 over 7. Set B equal to the side length AD, which is 8. And set C equal to the angle in between these sides, alpha. In the previous part of the question, we found that alpha is equal to cosine inverse of 7 over 8. Typing this big expression into our calculator will give us the area. It's 17.7051. We were asked to find the total area of the quadrilateral ABCD. But as we mentioned earlier, this shape is split evenly into two halves, an upper triangle, ADC, and a lower triangle, ABC. We've just found that the area of the upper triangle was 17.7051, and by symmetry, the area of the lower triangle will be the exact same. To find the total area of the quadrilateral, all we do is add the area of these two triangles. When we perform the calculation and round to 2 decimal places, we come to a final answer of 35.41 centimetres squared. In part C, Ava is looking at tilings of the unit circle. We are provided with a diagram of the unit circle, and there's been 3 points labelled: O, P, and Q. We are told that the angle QOP is 45 degrees. To help visualise this, we should draw in the side QO. Something worth noting here is that QO is a radius of our circle. Since we're working with the unit circle, which has a radius of 1, we know that QO will have a length of 1. In the question, we are asked to show that the point Q has coordinates minus 1 over root 2, comma 1 over root 2. Well, the coordinates of a point correspond to the movements needed in the x and y axis to get from the origin to that point. We can visualise these movements if we drop a vertical line directly down from Q so that it meets the x-axis at a right angle. The horizontal x movement corresponds to this side length, and the vertical y movement corresponds to this side length. If we focus in on this right-angle triangle, we can use some trigonometry to find these side lengths. Focusing on the 45-degree angle, the sides in a right-angle triangle can be labelled with adjacent, opposite, and hypotenuse. The hypotenuse is the side opposite the right angle, which here is 1. The opposite is across from the 45-degree angle, and here that's y. The adjacent is the third side, and here that's x. In a right-angle triangle, the cosine of an angle is equal to the adjacent over the hypotenuse. Here, the angle is 45, the adjacent is x, and the hypotenuse is 1. If we type cosine of 45 into our calculator, we'll get 1 over root 2. The right-hand side, x divided by 1, simply simplifies to x. So we found that x is equal to 1 over root 2. We can find y in a similar way if we apply the result that the sine of an angle is equal to the opposite over the hypotenuse. In our triangle, the angle is 45, the opposite is y, and the hypotenuse is 1. If we calculate sine 45, we'll get 1 over root 2, and if we simplify the right-hand side, we can see that y over 1 is just equal to y. So we found that y is also equal to 1 over root 2. Now let's put everything together to get the coordinates of Q. We've shown that Q is located 1 over root 2 units to the left of 0. Since movement to the left corresponds to negative x values, we can conclude that its x-coordinate is minus 1 over root 2. We've also shown that Q is located 1 over root 2 units above 0. When we move upwards, it corresponds to a positive y value, so we can conclude that the y-coordinate is plus 1 over root 2. In question 10, we're presented with a diagram of a right circular cone. The top portion of this cone has been extracted to form a basin. We are given several measurements here. The radius of the original cone is 15 centimeters. The radius of the base of the basin is 12 centimeters, and the slant height of the basin is 10 centimeters. In the first part of the question, we must show that the length from B to E is 40 centimeters. The key to solving this is observing that we have some similar triangles in our cone. Let's focus on the triangles ABC and DBE. Both of these triangles have a right angle. They also share a common angle at B. And since the angles in a triangle always add up to 180 degrees, we can deduce that the third angle must match also. Since these triangles have the same 3 angles, we say that they are similar. A useful result about similar triangles is that the ratios of the corresponding sides will always be equal. In this question, we were asked to find the length of BE, and I've labelled that here as x. I've also written in some of the measurements that we were given. DE is 12 centimeters, AC is 15 centimeters, and EC is 10 centimeters. In the triangle DBE, the side opposite the right angle is x. The side opposite the angle at B is 12 centimeters. So the ratio of these two sides is x over 12. Since our triangles are similar, we know that this will be equal to the ratio of the same two sides in the triangle ABC. Well, in that triangle, the side opposite the right angle is x plus 10, and the side opposite the angle at B is 15. So the corresponding ratio is x plus 10 over 15. Now we have an equation which we can solve for x. To begin, we can multiply both sides by 15 times 12. Then we can multiply the brackets on the right. 12 by x is 12x, and 12 by 10 is 120. As the next step, we can group our x terms together by subtracting 12x from both sides. 15x minus 12x simplifies to 3x, and as the final step, we can get rid of the multiplication of 3 by dividing both sides by 3. When we perform the calculation, we see that x is equal to 40 centimeters. In the second part of the question, we must find the total internal surface area of the basin. Well, this area will consist of two components. The flat circle at the base of the basin, which I've coloured in orange, and the curved surface around the interior of the basin, which I've coloured in blue. Finding the orange area won't be too bad. All we have to do is find the area of a circle. However, the blue area is a bit more troublesome. To find this, we should look back at the original cone. If we find the total surface area of this full original cone, and then subtract away the curved surface area of this smaller cone, which I've coloured in red, then that will leave us with the desired blue area. Now that we've outlined our strategy, let's go ahead and actually calculate each of the areas. The first result we need to use is that the curved surface area of a cone is equal to pi RL, where R is the radius and L is the slant height. The original big cone had a radius of 15 centimetres and a slant height of 50 centimetres. Subbing these values in gives us 750 pi. The smaller cone, BDE, which I had coloured in red, has a radius of 12 centimetres and a slant height of 40 centimetres. Subbing these in gives us 480 pi. As I mentioned earlier, the curved surface area of the basin is obtained by subtracting these two figures. When we do this, we end up with 270 pi. To find the flat surface area at the base of the basin, we'll use the result that the area of a circle is equal to pi r squared, where r is the radius. We were told that the radius at the base of the basin was 12 centimetres. If we sub this value in, the area comes out as 144 pi. Now that we know the curved surface area and the flat surface area, we can find the total surface area of the basin by adding these numbers together. When we do this, we end up with 414 pi. We were asked to give our answer correct to one decimal place. Converting this to a decimal and rounding to one decimal place gives us our final answer of 1300.6 centimetres squared. In part 3, we must draw the diagram of the net of the curved surface of the basin. We must include enough measurements so that no further calculations are required to draw the diagram with a ruler, compass and protractor. The following fact is useful when tackling this question. The net of the curved surface area of a cone forms a sector of a circle. Let's go ahead and illustrate this idea on the cone we were given. Imagine that we grab a pair of scissors and cut a straight line from C to B. Then, if we unfurl the cone and push it down onto a straight surface, we'd get a picture like this on the right. The line, which we cut with our scissors, will appear on the boundaries on either side. The base of the basin, which I've drawn in as this pink circle, will correspond to an arc. The top of the basin, which I've drawn as a blue circle, would also correspond to an arc. The curved surface area of the basin will be the region between these two arcs. I've coloured that in grey here. Now that we've got the sketch of our net diagram, we need to make sure we label it with enough measurements so that it could be accurately drawn. From the previous parts of the question, we already know the side lengths. BE measures 40 centimetres and EC measures 10 centimetres. Adding these together tells us that BC is 50 centimetres. These side lengths are useful, but they don't paint the full picture. To be able to draw the diagram, we would also need to know the angle at the base of this sector. I've labelled that in as theta. To finish off this question, we'll need to figure out what this angle is. A useful fact here is that the curved surface area of the cone will be equal to the area of the sector in the net. I should emphasise that we're looking at the full cone here, not just the grey region for the basin. Well, in the last part of the question, we found the curved surface area of the original cone. It was 750 pi. If we equate this to the area of the sector in our net, this will allow us to solve for theta. If you consider the full 360 degrees of a circle, the area of the circle is pi r squared. If you don't have the full circle, but instead have theta out of the 360 degrees, well then you'll have theta over 360 of the area. So the formula for the area of our sector will be theta over 360 times pi r squared. The sector that we drew had a radius of 50 centimetres. We can sub this value in for r, and then simplify to obtain an answer of 2500 over 360 times theta times pi. Since the area of the sector must be equal to the curved surface area of the original cone, we can equate this value to our 750 pi and then solve for theta. Since both sides of our equation are being multiplied by pi, a good first step is to divide both sides by pi and cancel these out. Focusing on the theta, it's being multiplied by a constant, 2500 over 360. To get rid of this multiplication, we should divide both sides by this number. Performing the calculation on the left brings us to our answer here. Theta is 108 degrees. In part B, Seamus is picking a new 4-digit PIN code. We're told that each of the digits must be between 1 and 9 and that no digit can be used more than once. In the first part, we must work out how many such codes are possible. It's useful here to consider choosing the code 1 digit at a time. We can visualize this by drawing out 4 empty boxes and then thinking about how many valid ways there are to fill in a digit to each of the boxes. Focusing on the first box, we have 9 choices for what we could write in, namely the digits from 1 to 9. When we consider filling in the second box, we're going to have 8 choices. This is due to the fact that no digit can be used more than once. Whatever number we put in the first box will be blacklisted and no longer available for use in the second box. By the time we move to the third box, we've already used 2 of our 9 digits, 1 for the first box and 1 for the second box. This means that there'll be 7 choices remaining for the third box. In a similar fashion, when we reach the fourth box, we've already used 3 of the 9 digits. This means that there'll be 6 choices left over when we're filling in this final box. To get the total number of choices here, all we have to do is multiply together the number of choices for each individual box. This gives us 9 times 8 times 7 times 6, which comes out as 3024. In part 2, we must work out how many of these codes contain the digit 2. A nice way to approach this is to try and find the number of codes without the digit 2. This can be done in the exact same way we worked out part I. We'll lay out 4 boxes for our code and think about the number of valid choices for each box. Since we don't want to allow the digit 2, we're going to have 8 choices of digit for the first box. 1, 3, 4, 5, 6, 7, 8 and 9. Similar to part I, each successive box will have 1 fewer choice than the previous box. This is due to the fact that we're not allowed repeated digits. So each time we write a digit in the box, it rules that out as a choice for future boxes. So the total choices for the number of codes without the digit 2 will be 8 by 7 by 6 by 5, which is 1680. In part 1, we saw that there was 3024 total codes. We found that 1680 of these do not contain the digit 2, so the remaining 1344 do contain the digit 2. In the final part of the question, we need to figure out how many of the codes have the sum of the first 3 digits equal to their 4th digit. The first thing to observe is that most of the time, when you add together 3 digits, you end up with a 2-digit answer. For example, if you added 4 plus 6 plus 7, you would get 17, which is a 2-digit number. If we want the first 3 digits to sum to the 4th digit, this implies that the sum must be a 1-digit answer. And there's not too many ways this can happen. We're also working with the restriction that we're not allowed to repeat digits, and that just restricts the possibilities further. In fact, there's only 7 valid ways you can add together 3 distinct digits and end up with a 1-digit answer. I've listed these here. 1 plus 2 plus 3 is 6. 1 plus 2 plus 4 is 7. 1 plus 2 plus 5 is 8. 1 plus 3 plus 4 is 8. 1 plus 2 plus 6 is 9. 1 plus 3 plus 5 is 9. And 2 plus 3 plus 4 is 9. We have to be careful here. Our final answer won't be 7, and that's because we have to consider the ordering of the first 3 digits. As an example, consider the sum 2 plus 3 plus 4 is 9. We have to think about how many different ways we can arrange the 2, the 3 and the 4. If I start with the 2, there's 2 options to finish off, 3, 4 or 4, 3. If I start with the 3, there's also 2 options to finish off, 2, 4 and 4, 2. In a similar way, if I start with the 4, we again have 2 options to finish off, 2, 3 or 3, 2. In total, we have 6 distinct codes being generated from our sum. So, putting everything together, we have 7 different sums, and each one generates us 6 distinct codes. The total number of codes will simply be 7 times 6, which is 42.